Okay, I have the device with me. As I told you, the device is the CT analyzer. I will show it to you, but I just want to show you from here the device from the side. You have the device here, just the power supply is on or off, and here you have its plug, and here you have the grounding point, which is what he told you is the equipotential bonding conductor. That's where you connect it to the ground point. And here, instead of working through the keypad or the device itself, you can connect it via your laptop so that you can connect to it or control it. I will conduct the test with you in both ways, once in this manner and once using the device itself. So let's take a look together. All right, let's open our device and talk about it here. As you can see, engineers, this is my device from Omicron. This is the CT analyzer device, which is great. Even if you want to see the device from the side, as I mentioned to you, here is our device. Here is our device. This is mine, and I have this one, which is mine too. Of course, I have the 3-phase plug here. And since I have set up the device, I don't have any issues. I have 2 ways to connect here, either the first method or the second method, which is with a connector similar to the one I am using. In addition to having a microcard here, or rather a memory card, which means you can store the results securely on it, remove the memory card safely, and insert it into your computer to retrieve and review your test results in detail. All right, I will talk about this device both manually and automatically using both methods. Very nice. All right, as we can see here, engineers, this is my device, which we mentioned is called the CT analyzer. Okay, it helps you here in the CT analyzer and draws the connection diagram for you. It has drawn the primary shape here. This is the primary shape, and it has drawn your file here, which is the secondary. All right. And here it shows you the 2 ends of the primary and here the 2 ends of the secondary, all right? You have here this inner part, or this part here, it writes for you what the primary is. Here are the 2 ends of the primary, and here is something called the secondary, all right? And here is something called the output. Beautiful, very excellent, okay? Now I am working with a CT analyzer device, and the CT analyzer device works with the IEC standard system. It is very nice. The IEC standard means that I am working with subtractive polarity, meaning that the polarity is always subtractive, So now you have your 2 terminals. Here is one terminal, which is connected here to the first terminal, the one in red, or what is in red. Nice, very good, okay? And you have the second terminal, which is connected to the black color. Nice, guys, very good. Okay. Here, we will find the killer. We agreed that the mark point or the dot point is here in our diagram, and when we talk about polarity, here it is. When we said that if I am talking about subtractive polarity, the dot points are next to each other, meaning if there is a dot point on B1, there should be a dot point on S1 to determine the directions of the planes, not how. So here, a device did the same method. Isn't this end connected to the red one? All right, so take the opposite end and connect it to the red end here as well. All right, and the other end is connected to which end? The black one. So that means if I connect this end, which is the red one, then I should also connect this end here, which is also red. And if I connect the second end, then who should I connect this to? So this one here, and that one there, who, and the primary and the secondary. All right. So with this, there are 2 ends connected to it, justified by the name, which is nice. So I will connect in the same way. To connect like this, here is my thing. All right. Here is mine. As you can see here, it is written here, who. All right. So the other side for me is who. It is. All right. So this is for me. Hold on a moment. Here it is. So I have this here as P1, and on the other side, I have P2. So what I did was, I have my cable, which is the green balloon here. The whole idea is that this cable has 2 ends, and these are the 2 ends. This one is connected towards P1, and the other one is coming out from the other side. I just wrapped the wire and brought it here with the 2 ends. So the end that is towards P1, I connected it to the red port and the other one to the black port. Is that clear? Very good. Now, if I come here, guys, I'm not sure if it's visible to you. Here it is. This is what we call the terminal box of the current transformer. This is the terminal box of the current transformer. As you can see, there are 3 terminals here, and here there are 3, and here there are 3 terminals. 3A, 3 terms, 3 terms, 3 terms. This terminal is labeled here, or inside here like this. If you look here like this, it is labeled 1S1 here like this. 1S2, 1S3, then the one above is Zabit, 2S1, 2S2, 2S3. So 1S1, 1S2, 1S3 belong to the first core, and 2S1, 2S2, 2S3 belong to whom? They belong to the second core. Nice, guys, that's good. Okay, let's go back here again. Hold on, guys, let's get involved, guys, with us. Nice, very excellent. Okay, now what have I done so far? All I did was take the core, and now I will test the first core. So I took the one that was and took the other one that was fine. Is this good, guys? Here it is. Stay with me and with me. And I have a secret. Oh, sorry, 1S, 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 3. So this means, guys, that I also took the big one, which is A over 1 in the first core. And the first core, based on what we took yesterday, is a core. What is it? It's a beautiful core, guys. Nice. Okay. So now I'm done. I've got P1, placed it here, and the other end is P2, which is the wire. I wrapped like this. This is the part of my cable or my bus bar. And for me, regarding the secondary, I will now test the first core, which is the protection core. The protection core. I will take a large one from it, which is basically the first one, which is the number, which is the tab number. So I connect it here. And of course, I connect it here above. So now what am I? Now I am ready with my connection. So how will my test be conducted? So let's zoom in on the screen. For what reason? What are we going to focus on now? Our screen will look like this. I think things are clearer now. Excellent. Very good. Hey, okay, let's see how things go, guys. The topic is quite simple. You see in front of you a set of cards that we call the card. Here, the first thing is called the city object. This card is entry data, meaning it's a set of data you input into the city analyzer so that it can recognize the system it is working in. So this is a set of cards. This is a set of data you input to familiarize it with your object and so on. Oh, then you will find its name here. And then, oh, a bot will exit your test and write your data here, such as your results, for example, or then excitation, then ratio test, then something called assessment. Nice, very good. Okay, let's go step by step. The first thing is to go here to the location. The location here tells you to write anything you want so that when I come to meet you, the report at the beginning and the end, I will know. For example, here I can write the location as any data I need. What does that mean? Here it tells you, look, did you notice here the word location next to it? There is something called details. If you press this button, here it is. It will tell you to write the name of your company, write the country you are in, the name of the station, the name of the feeder, the phase you are working on, if there is any ID for the phase, a definition for the phase, and so on. This is what the engineer means by the data. He wants to bring here or write down here. Nice, very good. Okay, and then you come here to the word object. Here in the word objects, don't forget, if you click on the word details, it will ask you who the manufacturer of the current transformer is, what type of current transformer it is, the serial number, which core you are testing, core number 1 or number 2, and which tap you are testing, 1S1 or 1S3. You write it here, and so on. So all of this, for you, these two things are just data, so that when you come to print the report, what's the matter? The matter is that it will print with all the complete details about this current transformer. Is that clear, guys? Good. Okay, I will show it to you. When we write it on the software, it will be easier. But for now, I'm just showing you here on the screen. Great. Okay, then it comes here to tell you what? It tells you the current, how much is the primary current. Okay, let's do our test now. Didn't we just say it's 1,000 to 1? Good. So all I'm doing is using the cable, just so you know what I'm going to do. Here we go. I'm just going to use this cable of mine. Leave it here. By God, here it is, 1 followed by 3 zeros, and I press enter. Then I go here and it tells me the secondary current. How much is the secondary current? So I tell it, by God, the secondary current should be 1 ampere. So there are some options here, meaning I can write one for it. All right, but I have some options where it tells you a question mark, meaning you leave it, and the device will check, meaning it will verify the values and see how much the secondary is and tell you. But you can choose 1, 2, or 5 for it. Then after that, at the end here, you find what? You find like 3 dots here, like this. 3 dots, meaning if you press this button, it will bring you down to another list. 1 on device 3, 2 on device 3, 5 on device 3, and so on. So of course, who do I need? I need the 1 ampere. So I pressed 1000 on 1. Okay, after that, I will go down here, my standard, any standard. By God, based on my email yesterday, we have the standard, which is 61, 800, or 869. So I will choose it. And then it will come and tell me, is it protection city or metering city? I will come and tell it, by God, this is protection city. It will ask me if it's a protection city or a metering city. I will say it's a protection city. As soon as I selected protection, look, I made an inquiry. Look here at this data. As soon as I tell it protection, it immediately changed and told me the class is something like 5p, 10p, or I don't know what. So I told it I want 5p, and it said, okay, the accuracy limit factor is what? It has it here, and when you go down, you'll find 20. I will tell it 20, and all these options are included in it perfectly. Okay, and it also has the burden here. What's the burden, engineer? Well, the burden is written as 30 volt amperes. All right, as soon as I told him 30 volt amperes, he immediately considered it for the measuring device or the protection device that will be connected, approximately 0.8. This is standard. As soon as you go above 2.5, 100 volt amperes, meaning as soon as you tell me 5 volt amperes and you're going up, it immediately takes 0.8. Great, nice, okay? And there's another burden. What's the difference between volt amperes and burden? Aren't they the same, engineer? Both involve the same data of mine. Very nice, okay? So what's the matter? What's the idea? Let's understand what the idea is. The idea, quite simply, is that based on the equation we talked about yesterday when discussing our factors, whether it's the accuracy factor or the safety factor, we said that the knee point voltage equals a certain factor in the secondary current in the RCT plus the burden, which is the rated burden, and we agreed that in the protection core, the knee point is supposed to be a fixed value according to your core. So this fixed value is a specific number, and the secondary is, for example, 1 ampere, and the RCT is constant and won't change with you as the current response remains the same. We said there is an inverse relationship between the accuracy factor or safety factor and the burden factor, or the factor with the burden. So we said, well, now the definition is that when I tell you 5B20, it means that here it tells you that the CT, as a manufacturer, the CT is following the standard. It tells you that the CT will reach the saturation stage and the core will reach the knee point voltage when at a number of times the current greater than 20, which is the accuracy factor, which is greater than the accuracy factor if the rated burden is what is expanded secondary circuit transformer. But suppose this burden was small, then the knee point will increase. And if this increases, then it will decrease, right or wrong. You told me that's correct, okay? Very good. So why did you introduce it here? He said, well, I will give you the allowance that your cone is actually connected to a circuit. And you have in the station this circuit, for example, a circuit from the beginning to the end over a long distance. So the resistance of this entire distance or the entire distance itself. Here you can simply say the operated burden, which is the actual burden you have. And based on that, I will tell you in this case what your accuracy limit factor should be. In other words, let's make this bigger. Let's say, for example, that it became 60. In other words, when I came to pay my burden installment, I found it to be 60 volts or 60 volt ampere. What do you mean? 60 volt ampere. Let's see how it will actually affect our results or what exactly we will understand from it. Great, very nice. Okay, is there anything else here? Yes, the frequency is at a full frequency of 60 hertz. Okay, is there anything else here? No, that's it. After that, I don't need anything else. But before I continue, I need to understand very well what exactly the device intends to do for me. The device is now going to perform a series of tests, right? Among them, the first thing I have is the CT ratio. Okay, Engineer Rashad, sorry, but this screen is done. You don't need anything from it now. We will go back to the test again. How are you going to perform the CT ratio? You are inputting the CT ratio as 1,000 to 1, and at the same time, you're giving it the CT ratio as 1,000 to 1. And at the same time, you're connecting the banana light set or those thin test wires. How is it going to handle 1,000 to 1? Honestly, I could trick you and say, no, it's going to handle how much? No, it's going to handle, for example, 100 amperes. But honestly, this can't handle 100 amperes. Or for example, it's going to handle 50 amperes. But honestly, this can't handle 50 amperes either. So how do you know if it will handle 100 or 50 or exactly what? How did you even know? Did I specify any injection value here? Of course not. So what's the idea then? The idea, engineer, is that the CT analyzer doesn't actually inject 1,000 amperes of current. So what does it do? It comes to its primary and injects engineers into the primary and secondary without injecting currents between them. So what does it do? It injects. Now, what will the current do for it? It will create a magnetic field, which are the magnetic field lines that are supposed to cut through what? Cut through the secondary windings, right? Am I wrong? Good. Okay, we all know that. We all know that in the end, this flux is a result, or if I told you that the EMF equals N phi times N times phi, 4.44, N phi times F, and we all know that in the end, the flux is inversely proportional to V over F, right? Tell me if I'm wrong. So I'll tell you, fine, what will I do? I will inject voltage in such a way that I generate, almost the same flux that would be generated if there were 1,000 amperes passing through my current transformer. This time I rely on the EMF and not on the 1,000 amperes that are supposed to generate, as the device knows how much flux it should generate. So what will the device do? It won't solve anything. A very low quality connection, okay, a very low quality connection with a low frequency so that V over F generates a flux whose value is equivalent to the flux value that the 1,000 amperes would have generated. So that's it for the ratio. As for the priority, it's the same idea. That's it. It's done. You have achieved a different voltage and frequency. And of course, a current has passed, but obviously with low values. What matters to you is that the current that passed generated the same flux that would have been produced if you had 1,000 amperes. That's good. It measures the angle between the primary and the secondary and determines the polarity based on that. Okay, so that's for the ratio and the polarity. As for the excitation curve, well, the matters are simple. Why are things simple? Because you told me yesterday that the matter here is straightforward. Aren't we aware that the more the current increases, its transfer will occur? And when this current transfers and passes through this entire resistance, a voltage is generated here. So the more you increase the primary current, the more the voltage here will increase. As the voltage here increases, it will continue to rise until it reaches a saturation point. If the voltage here increases by 10%, the excitation voltage drawn here in the core itself will increase by 50%. So he told you, I will do something very simple. For me, as a device, I will not inject anything into the primary. I will leave it open. All right, and as for the terminals of this, I will come to you. You have connected me as a device now, and there is no load. Do I have any protection or metering device connected now? No. So as a CT analyzer device present here, I will connect two terminals here like this on these two terminals and inject voltage here. What will I inject here? Voltage. And I will raise the voltage and measure the current, raise the voltage and measure the current, and raise the voltage and measure the current. So what is the current being drawn? What is the current being drawn now in this circuit? This circuit now is completely disconnected and not connected to anything. So the current being drawn in the entire circuit is just the magnetizing current of the core. So I will inject voltage and measure the current, inject voltage, and measure the current, inject voltage, and measure the current. Of course, the current is measured in series from within the device itself. And every time I inject voltage, I increase the current until I find a 10% increase in voltage, corresponding to a 50% increase in the drawn current, which represents only the current. I will draw these characteristics for you and tell you immediately what the point voltage is. That's why I needed the output voltage generator here, meaning this output is what injects into the secondary. as you can see, it is parallel with it, injecting into the secondary along with it. The last thing you also need is what? It's the resistance of the coils, okay? And what do you want from the resistance of the coils? I want to inject current into it and measure the current correctly, right? So to inject current, what will you do? You also need the output generator to inject current from it and measure the current. Or for example, inject current from the secondary and measure the current through what? Through the output, exactly. Now, someone might ask, engineer, why didn't he just make a jumper from here to here and here to here? Why did he connect both to that point over there? I'll tell you, simply because that would be a wiring mistake. What does a wiring mistake mean? Let's understand together. Engineer, you have a resistor here, right? A resistor, exactly. You want to ask what the resistance of the coil is, right? Okay, now you have two terminals called output and two terminals called secondary. What are the output terminals? Exactly. Here are the two ends of the Obot, and here are the two ends of the Aye. And here are the two ends of the Alexandrian. This one is called Obot, and this one is called Aye Alexandrian. All right, now, engineer, I have connected these two Alexandrian ends, and let's assume now that these are what will achieve for you who the current is, okay? So I have connected them here like this. Great, very nice. Okay, if I now had this voltage connected to these two ends in parallel here, what would happen? The current is not in this loop. And when you measure the voltage between these two ends, it means you are measuring the voltage across this entire resistance, including the resistance of the two wires of your test. Is that right, or am I wrong? You told me it's right, but that's not correct. I only want this resistance. So if I connect this here and this here, then now the current flows, stops at these wires, loops here, goes like this, and returns like this. But when I measure the voltage difference, I measure it only across this resistance. What is this resistance? This resistance only. So what is the correct choice for me? All right, that's one thing. The second thing is, as a steady resistance, the other thing is that my equation, the equation specific to my circuit, is the one we talked about. This equation, engineer, if my test result for the RCT increases, it means it will affect the factor and make this factor low. Consequently, I might find that my test result could be incorrect due to a wrong connection regarding what? Regarding the measurement of the CT resistance, because this equation tells you this is only the CT resistance, the resistance of the CT winding. But when you made an incorrect connection, you measured the resistance of the windings plus the resistance of the wires, and thus the total resistance increased here. Consequently, this factor also has to do what? It decreases. So it might tell you that this test is what? This test is not accurate. Very nice, great. Well, this is not a one-time thing. If I'm simply talking about test after test after test. But as we know, any resistance in the world, the resistance of the conductor is affected by temperature. That's why I need to tell it now, what the temperature is. So what's happening, engineers, is that the resistance you're measuring now, for example, if I'm measuring it here in Saudi Arabia where it's very hot, or you're in the UAE with different conditions, or someone in Korea with different conditions, or someone in Egypt with different conditions. So I measured the resistance and it came out to 0.1 ohm. You got 0.2 ohm, someone else got 0.15 ohm, and another person got 0.05 ohm, and so on. Someone else got 0.5 ohm, and so on. Who among us is correct? Yes. Here, engineer, there's no such thing as who among us is correct. What you need to do is go to a specific setting in our device. You go here and press on it, and when you go here, you go to something called, and you tell it, then you go to something called, then you set the ambient temperature of the environment you're currently in. For me, it's 18 degrees. This is your ambient temperature. But there's something called the reference temperature, which is always according to the ILC standard. And it's 75, the standard is 5, 6, and 3, 3, 3, 3, 3, 3, 3. And 3, when the manufacturer engineers produces the current transformer, they tell you that the resistance of its coils is based on their calculation, which considers factors like the number of turns and all that. They tell you that this resistance equals a certain value at 75 degrees Celsius. This means that my calculations, which include the specific resistance of the material, the length of the conductor, the cross-sectional area of the conductor, the number of turns, and everything related to the manufacturing of this conductor, should not exceed this resistance value at 75 degrees Celsius. You then go and measure it, as I will measure it now, at 18 degrees. Okay, that's good. But you use 18, and someone else right now, for example, in Australia, has a different temperature, and another person in a different place has a different temperature, and so on. So each of us has different temperatures. Therefore, we must all refer to a single reference temperature, which is 75 degrees. When we go to 75 degrees, what does the device do? After measuring, the device currently measures at 18, which is the temperature of the actual environment we are in. Then the device multiplies it by an internal equation, which is 234.5 plus 75, meaning 234.5 plus the temperature of 18. The important thing is that it multiplies it by the amount of R, which it calculates to get the amount of R at 75 degrees. And this equation, of course, has a proof. I am present with you even in the manual of the set analyzer that I sent to you. And this equation is also included in it. Is that clear, guys? So in simple terms, what is the topic of degree? The topic of temperature. I press back here like this. Done. I am now ready to conduct the test. All I have to do is this. All I have to do is just come here to this on and off button and just tell it what. Okay. Let me show you the script here. I will press it in front of you so you can see what the script is.